we propose Tensorial Radiance fields, or TensoRF, a novel scene representation that enables photorealistic rendering, fast reconstruction, and compact modeling simultaneously. We model a 3D scene as a radiance field inside its bounding volume. We consider this radiance field as a high-dimensional tensor and propose to decompose it into compact low-rank tensor component factors as our scene representation. Here, in this example, we factorize this field into multiple vector and matrix factors. These factors encode the entire scene content in their different spatial dimensions. They are used with the sum of vector matrix outer products to model the scene as a volumetric radiance field expressing the scene geometry and appearance along their corresponding XYZ axis. In a sense, these vector and matrix factors are used to compute the volume density and RGB view-dependent color at any 3D scene location, allowing for rendering at arbitrary viewpoints with differentiable remarching. Our approach achieves super-fast reconstruction, compact scene modeling, and state-of-the-art rendering quality. As shown here, with the results on the Blender dataset, our approach outperforms previous and concurrent works from multiple perspectives. Here, we show our optimization process on this LEGO scene from scratch. The corresponding training steps, time, and testing PSNRs are shown on the right. Note that our model starts to produce realistic images with very few optimization steps. Even with only 7,000 steps, taking less than 3.5 minutes, we already achieve high quality with a high PSNR. In fact, this quality is already better than NeRF's result, here shown on the left, which is trained for 500,000 steps taking more than 30 hours. If we continue training our model a little longer to about 15,000 steps, we can further boost our rendering quality with even a much higher PSNR, significantly outperforming NeRF. This reconstruction uses only 3% training steps used in NeRF and is finished in only about 8 minutes, corresponding to more than 100 times speed up. With a closer look, we can clearly see our results are of much higher visual quality with less outliers and more high-frequency details. TensorF also outperforms the concurrent work Planoxos that also aims to achieve fast radiance field reconstruction. Our method is able to reconstruct faster with a higher rendering quality as shown here. Note that Planoxos utilizes customized CUDA kernels to optimize a large number of training steps. In contrast, our efficiency gains are obtained with a standard PyTorch implementation. Optimizing our code with additional CUDA kernels can potentially further accelerate our reconstruction. On the other hand, Planoxos consume large memory because of using an explicit voxel grid. Our factorization-based model enables high compactness, leading to a substantially smaller model size. Specifically, our radiance field is factorized and modeled with tensor decomposition techniques. Potentially, any decomposition techniques can be applied in our general framework. In this work, we apply 2 decomposition techniques, including the traditional CP decomposition that factorizes a field into only vectors, and a novel vector matrix decomposition that factorizes the field into vectors and matrices as we shown earlier. In fact, by applying the traditional CP decomposition, we can already achieve efficient and high-quality reconstruction as shown here. Note that our CP model achieves super high compactness. Its model size is less than 4 megabytes, even smaller than NeRF that is purely MLP-based and known for its high compactness. In addition, our super compact CP model can also achieve better rendering quality and significantly faster reconstruction than NeRF. CP decomposition leads to super high compactness, but it can require a large number of components to achieve higher accuracy and complexity, which undesirably increases the reconstruction time. On the other hand, our novel VM decomposition contains more parameters in each component and reduces the required number of components. As shown in this example, our VM model can accurately model the scene with fewer components, leading to significantly faster reconstruction and much better rendering quality. In comparison with NeRF, these results from our VM model are significantly better in reproducing the high-frequency geometry and appearance details. Again, our reconstruction takes substantially less optimization time and fewer training steps. Our approach consistently achieves superior rendering quality when compared with NeRF. Here, our method is able to accurately model the high-frequency texture details in this chair scene. Although our VM model is no longer more compact than NeRF, our model is still of high compactness. When comparing with the concurrent work planoxels that uses an explicit voxel grid, our model size is consistently substantially smaller. Again, our approach is able to reconstruct faster and requires significantly fewer training steps than planoxels. As shown in this example, our results are also visually more realistic. Our method is able to recover the shape and texture details without any missing geometry. In addition, our approach can be also applied on forward-facing scenes by considering an NDC perspective space. In comparison with the previous state-of-the-art NeRF, our method achieves visually comparable and quantitatively even better results. Again, our method is faster by orders of magnitudes, taking substantially less optimization time and fewer training steps. In general, our Tensorial Radiance field achieves fast reconstruction, compact modeling, and state-of-the-art rendering quality on various challenging datasets. Please refer to our paper for more results. We now briefly discuss our technical details. Specifically, our Radiance field corresponds to a dense 3D voxel feature grid with paravoxel features. Each voxel contains the volume density directly and a multi-channel appearance feature vector. These appearance features and a viewing direction are sent to a decoding function that converts them to the view-dependent RGB color. For the results shown in this video, we use a small two-layer MLP as the decoding function. But our framework is also general and supports other types of functions. In the paper, we also apply traditional spherical harmonics functions, leading to a scene representation without any neural networks, and achieve high-quality results as well. Essentially, this dense voxel grid encodes a Radiance field. However, directly representing a high-resolution dense grid is inefficient and consumes large memory. Previous and concurrent works that use similar feature grids apply different 3D spatial structures like a hash grid or a knock tree to sparsely model the features. In contrast, we propose a novel tensorial approach that models the feature grid in a completely different way. In particular, we consider this grid as a four-dimensional tensor, where three tensor modes correspond to the XYZ axis and the fourth mode corresponds to the feature channel dimension. This allows us to leverage tensor decomposition techniques in Radiance field modeling. Potentially, our general idea of tensorial Radiance field can be combined with any kinds of decomposition techniques. In this work, we apply the traditional CP decomposition and a novel VM decomposition. CP decomposition factorizes a tensor into vectors of all three modes, representing the tensor as the sum of vector outer products. Each outer product of three vectors leads to a compact rank 1 component tensor. And recovering an element in the original tensor is very efficient and simply requires sampling a single value in each vector and computing the sum of scalar products. Here, for simplicity, we only show the vectors for the spatial XYZ modes. In modeling the full 4D tensor, we also have an additional vector in each component that expresses the feature dimension. As shown earlier, by applying the traditional CP decomposition, we already achieve high-quality reconstruction. However, because CP decomposition uses super compact rank 1 components, it can require a large number of components to achieve higher accuracy and complexity, which undesirably increases the reconstruction time. Therefore, we introduce a novel vector matrix decomposition that effectively reduces the required number of tensor components. In particular, unlike CP decomposition that purely uses vectors in each component, we use one vector for one mode and combine the other two modes by jointly modeling them in a matrix vector, and the component is expressed by a vector matrix outer product. This leads to three different types of tensor components. Each type combines two different spatial modes in matrix vectors. Here, recovering a tensor element retains simple and efficient. It still just requires sampling a single value in each vector and computing the sum of scalar products. In a sense, VM decomposition relaxes the low-rank constraints for two modes per component. Each component contains more parameters and is able to express more complex scene distributions. As a result, our VM decomposition leads to better rendering quality and faster reconstruction. Thanks for watching. Please refer to our paper for more details.